First, we will look at some of the improvements to dynamic simulation in the 2012 product. We will start by activating a level of detail, which allows us to remove small components from the assembly that would not have an effect on the overall results. One of the big changes made to dynamic simulation for 2012 is the ability to edit the automatically created joints, which are interpreted from assembly constraints. You can change the direction in which the revolution joint was applied. We are applying a torque load to emulate the load that the robot manipulator arm would see from the passenger compartment, which are the 4 seats rotating along the axis at the end of the manipulator arm. This also saves time and CPU cycles, as it allows you to significantly reduce the number of components which are required to obtain accurate results. Next, we will look at the 2 most significant seconds of motion taken from the movement profile for the manipulator arm during the course of the ride. We are basically breaking up the 2 seconds into segments of motion. We are moving about 69 degrees per second, which is the maximum rate of rotation for this manipulator. There is a 180-degree change of direction, essentially going from positive 69 degrees per second to negative 69 degrees per second in the opposite direction. We can also change the rate of curvature or the nature of how the load is applied, whether it is instantaneous or gradual, which is what we were doing with that curvature. Next, the manipulator will be run through its range of motion for the 2 seconds. When it is done, we can use the output grapher to look at the nature of the forces, which are generated in more detail. This is the joint on which we applied the profile to. You can review a lot of results here. Notice the velocity curvature itself as well as the force. You can also look at the position. Basically, it went in one direction and then halfway through the rotation, it changed to the other direction. But we are going to focus instead on the forces which are generated. Taking a look at curve properties allows us to see the minimum, maximum, as well as the total delta. We are also able to isolate and search for the maximum load at any point in the curvature. You will see that the model maps to the point on the output grapher that we select. If we search for maximum forces that occur at 1 second through the animation, we can tag that 1 second time slice and export that to FEA. This allows us to export those loads directly to the base of the manipulator, which is essentially what we want to test. This relieves us from having to perform time-consuming calculations, such as a free body diagram, to figure out what those maximum forces are. In this case, we used dynamic simulation to find the maximum forces, and then we entered the stress analysis environment and imported the motion loads from dynamic simulation. Those motion loads are going to be the peak loads that occurred at that exported time slice. At this point, all that is left to do is to set up the static environment for the base of the manipulator. We start by grounding the base to describe how the base itself is mounted to the car of the entire robo-coaster segment. You can select the faces themselves, which are bolted down, as well as the bolt cylinders. These are the cylinders of the holes, which the bolts pass through and therefore represent the portions of this part, which do not move. Now we are going to specify our mesh settings. We will specify a mesh that is a bit coarser than the default. The reason for doing this is that we are looking for trends. If we wanted something more accurate, we could do an adaptive mesh around the holes to make sure the holes themselves would be able to withstand the loads. But at this point, we are trying to make sure that the design of the top of the base, where the manipulator mounts to the base, is going to be able to handle the loads. You may have also noticed the use of curved mesh elements. This is used for when you have parts that are primarily comprised of cylindrical faces. It is advantageous to set that radio button, and what that does is puts the solver into a P element solve instead of a traditional H element solve, which is more appropriate for models that have a higher number of curved faces. Once this is complete, the only thing left to do is run the simulation. I will change to a view that lets us take a better look at this once we get the results. Now we will simulate this. At this point, if there were any problems with the model, the Simulate dialog box would report them. It runs the calculation fairly quickly through the model and through the solve. Notice the deformed view. I prefer typically to put that into actual view. You can see what our maximum loads are, our maximum displacement, and it is a little less than a millimeter, which for something as large as this piece, it is actually very, very good. The loads themselves are very low. This is well within the operating limit of the materials themselves. The safety factor is not as high as we would like it to be, but at 1.5 approximately, it is good enough. The probe tool allows you to essentially select areas of interest. You can see that the probed areas do update as we change the type of display from stress to displacement. The probe labels can be turned on and off at any point in time.